Welcome back. Today's Leetcode question gets at the use of a fundamental search algorithm for a sorted list. The problem asks to imagine a list of integers as a kind of mountain, and to locate in O of log n time the peak of this mountain, such that integers to the left and to the right are smaller than the number. We will assume that anything outside of the list can be considered smaller than what is in the list. Using a version of the binary search algorithm, we can make short work of what is considered to be a medium difficulty problem. Let's get started. In order to explain the idea of a binary search algorithm, consider a phone book. The names in the phone book are arranged in alphabetical order, and if we needed to search for a name, it would be possible to go and search through each name one at a time. Doing that, however, would be really slow. We might do this instead. Start at the halfway point of the phone book. If the name we need is not in the middle, do the following. If the name is past the middle, discard the lower half of the book. Otherwise, discard the upper half. With the remaining half, repeat the same procedure until your middle value equals your target name. Notice that the problem size is decreased by half after each iteration of the algorithm. The amount of computation grows logarithmically base 2. So we could describe the time complexity as O of log n. This is good news because now we will meet the time constraint of our problem. With that basic idea in mind, we can create a modified binary search that targets a number in a list such that the number is the peak. We start by defining L and R, which will be the upper and lower bounds of our search. The binary search part of our algorithm works as follows. With our upper and lower bounds, we define a mid-value that is in the middle of these two bounds, rounded down to the nearest integer. Then we check if the value in our array at mid is greater than the next value. If it is, we know that the peak must exist at or to the left of mid, so we set R to be mid. Otherwise, we know that the peak must be to the right of mid, so we set left to be mid plus 1. Once the left bound is not less than the right bound, it means we have zeroed in on our search. We can return the left bound, which now sits on the desired peak. As we mentioned, the time complexity of this algorithm is O of log n. Since we do not require any extra storage in our algorithm, the space complexity is O of 1. That is, the space will remain constant no matter how large our input list is. Now there's a short and sweet problem. Happy coding!